Welcome. So I'm going to, can you zoom out please, to talk about object algebras and how to use them to design, in the engineering sense, domain-specific embedded languages. Okay. So we are going to do all that. First, I'm going to introduce you the problems that led me to look at object algebras, then what they are, how I implement them in Scala, and I will highlight some of them properties, and finally I will pronounce the M word. I apologize by advance. So first, well, who am I? I'm this will be quick. So I'm basically a software engineer, and I've spent the last 5 years to essentially build web applications. So what kind of problems did I meet? Well, typically, you know, web applications are about clients and servers. So when they communicate, they have to agree at some point on a common protocol, communication protocol. I'm not talking about HTTP. I'm talking about the application level protocol, so that the requests performed by the client are correctly interpreted by the server. And when we want to have documentation for our web service, we also want to describe this protocol. So we end up having the implementation and the description of our protocol scattered and duplicated in several places. So that was the problem I wanted to resolve. So let me illustrate this with an example in Scala. So let's imagine we have an application for shopping that lets users get information about an item they want to buy, for example. So the important part is that on the server side, at some point we want to check whether an incoming request matches some pattern, and in such a case we call some business logic and then we return a response to the client. So now on the client side, that's the opposite. We want to build a request. So that's how we do it. And you see that indeed the way we build the request here, for example, in constructing the path item slash blah blah blah, the identifier, duplicates the patterns that we want to match here. And also the HTTP verb get is duplicated here and here, and also the JSON representation used by the client as server is duplicated, and so on. And if we have a system that documents our HTTP API, then, for instance, here, the description of the format that is returned by our server duplicates also the implementation of the server. So all of this must be consistent together. So that's a pain to maintain. So instead of that, I want to have just one language that I can use to effectively describe the whole protocol communication. And then I want to be able to derive from this language a client implementation, a server implementation, and to be able to generate documentation. So that's the goal, okay? But then I have an engineering concern. I don't want to do that for each project, each new application. So I want to be able to capture somewhere in a library, in a reusable library, the part of my language which are not specific to a given application, so that I can use it in which application. But then if I do that, I have another problem. I want to be able to integrate application-specific concerns in my common language. So I need a means of extensibility to be able to do that. Another motivation for extensibility is that we might want to be able to break down our whole language into smaller languages focusing each on different part, and maybe with some languages having more power than other, and maybe sometimes relying on some specificity on some interpreters. So that the idea is that the whole language is not damned down by the limitation of some interpreters. I will come back to that later. So object algebras are a solution to this problem. Object algebra are a solution that I did not invent. So here are some references that you can read if you like the topic. So all the credits go to these guys. So we have to start by first specifying the domain of our language. What are we going to talk about? So for the sake of brevity in this talk, I will focus on a subset of an HTTP API just on the path of URL. So a URL path is, for instance, /foo/bar/item/123abc or /item. So it's made of segment separated by slashes. So we want a language that allows us to define such segments and to combine them by chaining them. Okay? So we can translate this into what we call an algebra interface, which is just an abstract interface or a trait in Scala, which contains these two constructors, segment and chained. The first one constructs a path segment, and the second one chains together two segments. Easy. The return type here is A, which is an abstract type parameter. For now, we can see that this algebra interface as a kind of abstract factory that gives us the rules to create and combine paths. But the return type of this factory is unknown yet. As we will see, it will depend on the interpreters that we will use. But we can already use this algebra interface to define path. So we just define this method here. So say that we want to define the following path, item/123abc. Then we just have this method that takes as parameters the algebra interface, and then we just use the constructors. Easy. Then we have to define an interpreter. So an interpreter is just an implementation of the algebra interface. So when we implement an algebra interface, the first thing to do is to choose a concrete representation here for the carrier type. So here, from the perspective of the client, I want to build path, so I'm using a string as a representation for path. And then if I apply this interpreter to some item path, I get the following path as expected. Okay. Then, from the server side perspective, things are different. Okay, that's a sign that there is too much code on this slide. So the job of the server is to process incoming requests to check whether their path matches or not the definition of a path. So here, as a concrete representation, I'm choosing a function that takes as parameter the path of an incoming request and returns a Boolean. Okay? So now if I apply this routing interpreter to some item path, I get this function, and then this function, if I apply path candidate foo/bar, I get false. And if I apply item/123 ABC, I get 2. So that's it. Easy. So far we defined an algebra interface that gives us the vocabulary of a language and tells us how to define concepts and to combine them together. And then we define interpreters to give several meanings to this vocabulary. Okay? We just needed abstract methods and inheritance and type parameters. You can do that in Java, Java 5. Okay, so let's do some more sophistications. In practice, when you have algebra interface, um, when you have a richer language, you end up having several carrier types because you will have you want to use one distinct carrier type per concept. So if you have the concept of path and then the concept of query string and then the concept of URL, then you will have 3 type parameters here, and that will be a pain to use. So instead of having type parameters in Scala, you can trade them for type members. So here I just removed the type parameters and replaced them with abstract type members, so path, query string, and URL. Okay. So why is it more convenient like this? Look at use site now. When I take an algebra interface as parameter, I don't have to specify all these type parameters again and again. That's just the point. How to support syntax? We can do that in Scala by adding an upper bound constraint to our abstract type member. So we say that this path is abstract, but it has to be a subtype of this path syntax. And this type is implemented here, and it defines a symbolic alias for the chained combinator, so that interpreters will just mix this trait into their concrete representation. And at the use site, we can just use the nice syntax here with the symbolic slash instead of having to write chained, for instance. Okay? This one is a bit more complex. So until now, the path that we were able to express were all constant. It was like slash foo slash bar slash item slash abc123, but we were not able, with the model I presented, we are not able to describe a path which is made, for instance, of one segment slash item, for instance, followed by any string segment, any segment containing a string information. We can fix that by making a path a type constructor. So here, that's my algebra interface. My type path here takes now a type parameter A. And I introduced 2 new constructors, string segment, which returns a path that carries a string information, and integer segment, which returns a path that carries an int information. And I updated the chained combinator so that it carries a tuple of both the first path and the second path. Okay? So now I can define a path that takes describes any string segment and then any integer segment, like this. For example, if my items can be located by first a name and then an integer identifier. Okay, but let's look at the consequences on the interpreter side. So now when we choose the concrete representation of our path type, and for instance for the client interpreter, we have to say what does this A information means in the perspective of the client. And from the perspective of the client, this information is the information that is needed to build a path. So we use a function from A to string to represent a path. So now if we apply this interpreter to item and then we apply this information, then we get the expected path. But from the server-side perspective, the situation is the opposite. The A information is what is extracted from an incoming request, right? So we use a function from string to option of path to represent our path. So if we apply this interpreter and then we apply this candidate path, we are able to extract this information. But then if we apply this candidate path, we are not able to extract any information because bar here is not, an integer. Ooh. Okay, I stopped it. Now some interesting properties of object algebras. The first one, extensibility. That was actually the main point of object algebras. They were initially designed as a solution to the expression problem. It means that we can extend an algebra interface in both directions. We can retroactively add new vocabulary. So for instance, we can extend the URL algebra interface and introduce the concept of request by defining a trait which extend the algebra interface and which introduce new abstract members. That's it. So here, this get method means a request, an HTTP request using the get method. And we can also implement interpreters. We already saw some of them. So here is another example, an interpreter that produces an HTML page documenting the API. So again, an interpreter is just an implementation of an algebra interface, and both interpreter and specialization of an algebra interface can be implemented independently of the algebra interface itself. Okay? And in the case of Scala, because we have multiple trait inheritance, we really have this ability to define a composite language from several pieces that we pick together, and then we are also able to define a composite interpreter for this language by picking the interpreters of this language and combining them together. So that's very powerful, actually. Modular expressive power. This property is very interesting, but a bit complex. So I'm going to explain it on top of this version of the algebra interface. The one that takes here this type parameter A for the path carrier type. So let's say I want to refine this algebra interface, and I want to say that the path carrier type must be an applicative functor. I can do that by extending the algebra interface and introducing this abstract member of type applicative of path. So it means that at some point, interpreters will have to give an implementation of an applicative of path corresponding to the concrete representation they use for path. Okay? And at use site, users can benefit from the expressive power of applicative functors to manipulate path. For instance, we can already implement the chain combinator using the map2, sometimes known deep-with combinator that comes from the applicative functor. Or we could also say that the path type must be a monad. So again, we extend the algebra interface and we define this abstract member of type monad of path. And here, because the monad is also an applicative functor, I'm actually extending the applicative interface rather than the path interface. So what's the point of all that? We will see in a few slides, don't worry. Then from the at the interpreter side, we have to implement, we can, well, the goal of an interpreter is to be as powerful as possible. It's to implement a language as powerful as possible. So in the case of, for instance, the routing interpreter, we can implement the monadic interface, so we do so. So here I'm using, as a concrete representation, a kind of state monad. But then we see that in the case of the documenting interpreter, we cannot actually implement the monadic interface because our concrete representation is just a string. So we cannot implement a monad of path if path of A is a string. You can try, but okay, We cannot implement a monad, but we can implement applicative functor. So let's do it. Well, what's the point of that? Now, at use site, when you write a program, maybe sometimes you need only the expressive power of applicative functor, and in that case, you will require as parameter the applicative interface. And maybe sometimes you need the expressive power of a monad, and in such a case, you will require as parameter the monadic interface. But the consequence is that the second program here can be interpreted by less interpreters, because not all interpreters are able to be monadic, basically. So the conclusion is that the more expressive power your program requires, the less interpreters you can apply to it. So pick the least powerful expressive power you need. Last, DSL families. That's the ability to encode subtyping relationships between carrier types. So here, for instance, I'm saying that the path type must be a subtype of the URL path. Okay. So what's the point of that? Well, in practice, it's useful to specialize some DSL and to add new capabilities to it. For instance, here we can say that both URLs and path can be seen as URLs, but only path have the ability to be chained together. Okay. So if we put things together, what time is it? Okay. Initially, we have this problem where we had a client and a server which were duplicating things. So I wanted to be able to capture the essence of the HTTP application level protocol on top of HTTP, so that I do not hard code things both in the client and in the server. So first, I want to capture the fact that I'm using the HTTP verb get and using this URL pattern. So I can do that with my language as follows. And then I can replace the server implementation by applying the routing interpreter to my path, to my endpoint definition, request definition. And also I can remove some code of my client code by applying the client interpreter to the request specification to read an item. Okay? And I can also get automatic documentation from my system by applying this interpreter to my read item request thing. So last, comparison with Freeman ADS. So initially I wanted to do a deep comparison, but it was too long, so I shrinked it. So here is the first attempt to explain what Freeman ADS are in just one slide. So Freeman ADS abstract over the monadic context of a DSL interpreter. Well, how does it work? In practice, you start by defining your language as a data type. So the constructors of your data type are the same as the constructors that we have in our algebra interface, actually. Okay. And then you wrap your data type constructors into the free monad so that users can use them and write program with them. And at some point, you will implement interpreters to actually do something useful with your DSL. And your interpreter, in the case of the free monad, has to be a monad. So because users can use your DSL without binding it to a given interpreter, I'm saying that free monads abstract over the monadic context of the interpreter of the DSL. Okay. So I kept only one point of comparison. There are a lot of things that we could compare and tell about free monads and object algebras. So I kept only this point. So a key difference is that with free monads, your interpreter has to be a monad, while with object algebras, your interpreter can be a monad, but this is not required. So object algebras are actually more general than monads. And as we have seen in the modular expressive power section, the fact that free monads require the interpreters to be a monad reduces the space of possible interpretation for a given language. So in my example, only the routing interpreter was able to be a monad. And more generally, when you have dual interpreters, like a client and a server, then at most one of them can be a monad, but not both. So that's an important limitation, I think. So in conclusion, I think object algebras are a way to define extensible embedded DSLs in your programming language. And I think they are quite easy and natural to use in object-oriented programming languages, because they essentially rely on simple features of object orientation, like abstract members. And also, I think they are more general, and also, in my opinion, simpler than free monads. So that's why I think they deserve more attention from the community. So that's it.
Thank you for the talk. My question is, how do you compare this approach with cake pattern that is usually used in a similar way? Would you have
Which pattern?
cake pattern?
Oh, actually, that's very similar. I mean, in Scala, when you use object algebras, you end up using the cake pattern. Or, yeah, yes, that's very similar to the cake pattern. Actually, I think the cake patterns, the cake pattern naturally emerges in a lot of situations in Scala. So you might discover it accidentally in a lot of situations, and maybe this one is one of them. Yeah.
So first, I think there's technically interpreter for free monad is not a monad, is a natural transformation between monads, as far as I remember.
Yeah, but the target type of the
natural
transformation must be a monad.
Yeah, but itself is a natural transformation. And also a question, but that's not the question. The question is maybe could you compare to free applicatives, the object algebra approach?
Well, with free applicative, you have the same situation than here, which means that it requires your interpreter to be an applicative functor. And what can I say else? I think basically when you write DSLs in using the free monad style or free applicative style, well, today there is no tooling that helps you decide later if you want to use the free applicative, if you want your DSL to target free applicative or free monads. And here you can decide later. You have more flexibility in when you want to use one expressive power rather than another expressive power. I expect I answered your question. No other question? Okay, thanks.